basically discussed about the file system interface, the interface provided by the file systems. So what was files? We learned about what was file system, about partitions, about defined files, their attributes, and we also learned that what are the index of the files, because the files are sort of chapters in a book. Then the indexes are basically the index at the beginning of the book, and we talked about different indexing structures and how to make them efficient to provide more usability and at the same time ensuring no conflicts like some circles in the system, in the directory system. Now, in this lecture, we'll talk about the issues surrounding the file storage and how to actually implement these interfaces. Because ultimately the vendor will just give you a hard drive. You'll just buy a hard drive of 500 GB, 1 terabyte, 256 GB. It might be it might be a disk-based one. It might be an SSD. It might be a thumb drive, flash drive, whatever physical properties it has. But ultimately, you will just get a hardware. And your operating system will provide this file system interface that we talked about, this whole idea of files and directories and all those things. And we'll talk about that implementation in this lecture. And before we start today's lecture, we need a little clarifying background. So we call what is basically what you call RAM in your computer, 8 GB RAMs or 16 GB RAMs. It is technically called as primary memory, primary storage, or main memory. So that's why we call the hard drive or SSD or whatever you have, the larger one on your machine, on your computer, as secondary storage. RAM, primary storage, this hard drive, secondary storage. And in this lecture, or in this part, this is basically very last part of the operating system, but we'll tell you how we can write code for OS components, which can let you use this secondary storage efficiently, right? What is efficient? How to build an efficient file system. Now, the old way, you ultimately, like you are an OS developer now. Think about in that shoes. You got an hard drive, the disk, okay? And the old way to access this hard drive for your operating system was to tell the hard drive what data you want using physical addressing, okay? Which might sound like that hard drive will, give me the data from 5th track of 20th sector, which might actually sound gibberish to anyone except for the hard drive, even for the OS developer. Okay? That means that when you're writing an operating system, you needed to know the physical properties of the drive, because if there is a 5th track of 20th sector, whatever it is, you might not ask 25th track of 200th sector, because that might not exist on your hard drive, on the hard drive that your computer is using. What does it mean? In the old days, the operating system needed to know the physical properties of the drive, and that is one of the reasons IBM was creating these operating systems, because they are also creating the hard drives and the RAMs and the whole machine. They created the hardware, then they wrote the OS for those specific hardwares. And as you can see, the problem there is that only IBM will create computers forever. There is no Ubuntu, there is no Linux. You cannot really write an operating system which will run on a range of this different types of hardwares, different type of hard drives. So essentially, we needed, like when the modern operating system came into being, or research and development, there was a need for an abstraction. And the abstraction is a logical addressing of hard drives. So in this logical block addressing, the disk is abstracted as a logical array of blocks, 0 to n. And these blocks are smallest unit of data transferred to the operating system. And this is called a logical block addressing, or LBA. And we will call these blocks 0 to n, these blocks on secondary storage as physical blocks. So this is, I know this is a bit confusing because we just talked about logical blocks and then again talk about physical blocks. So think from an operating system's point of view. The operating system is asking the hardware, like all the operating system needs to do is to ask the hardware that give me the block from 25 to 35. So for the operating system, these 25 to 35 blocks of data, bytes or bits of data, they are basically your physical blocks of the hard drive that operating system can see. Operating system doesn't know about logical block addressing or anything. The first thing to know, not even know is that when you are writing code as operating system, then you just assume whatever is in between, inside, like underneath your or in your hardware, like underneath the operating system, it's basically a logical array of data blocks, 0 to n. And this abstraction, this logical array abstraction, is already provided by almost all of the hardware vendors. That is the reason, if you are any of you are into building computers or basically playing around with actually buying parts and then putting them in a frame, like in desktop or building gaming computer, you would know that people actually change your 5600 RPM hard drive, like this disk drive with 7 to 200, and with that, when the time comes, like when the price is low, you can modify it with SSD, which is a totally different technology, much faster. But the reason you can do that is that the disk exports its data to the operating system as a logical array of blocks. Any disk, they have the same interface, 0 to n. This is disk addressing, and this is the basis, like this enables the operating system to write unified code. Understand that. So we need to build a file system. So whatever ingredient is given to you as the operating system developer is a bunch of logical array of blocks, 0 to n, and then you want to build a file system to use these blocks for efficiently creating, storing, and retrieving files, and also deleting files. Okay. So let's start with given those logical blocks. So what you understood is that essentially as operating system, you have this abstraction that everything underneath is 0 to n, a bunch of blocks. So let's start with the structure of the file systems that you as the operating system developer need to create. Now, what should be taken care when you are designing these file structures? Two things actually. So when you are doing this file structure, like creating or basically doing anything with a file, there are two things involved, two steps. The first one is to find the logical storage unit, basically finding those blocks, the ith block where the data is stored, the actual data is stored. And then you also need to do some logistical, like some bookkeeping of this data, because this data will come with a collection of the related information. For example, file ID, like for a file, there is this data associated with the file, which will decide on the disk, like on some logical blocks. But in the disk itself, there will be some additional information associated with the file, like the file ID, the file name, the file creation date, and so on. Okay, so this related information to the files will also be stored on the secondary storage itself. Both of these things, both of these two things are stored on file system. So we will primarily consider our hard disk as secondary storage, and like this file system on secondary storage, they will provide the user like an efficient interface to the disk by allowing data to be stored and retrieved easily. Now, so a file system essentially solves two design problems, which is how to define a file and its attributes, like which one are the most useful, because I told like file ID and name and time of creation, but What about others? So which file attributes should be there? And they also define the operations allowed in a file and the directory structure for organizing files. Remember in the previous lecture we talked about what are the attributes of a file, what are the operations, and I promised you that if you do those 6 operations you can do almost all the tasks on a file. And also we talked about the directory structure of organizing files. So this is a job of a file system, some problems that needs to solve. The second problem is creating algorithms and data structures to map the logical file system that is available to the users into the physical secondary storage devices. So this physical, what we meant is that, so for there are 2 levels of abstraction. So for the operating system, the physical storage is a bunch of blocks, physical blocks. But for a user, when you are creating a user program, like, or for example you are opening your text editor to write some text, you are not really talking in terms of write this data from physical block 1 to physical block 200. You don't do that, you just write. An operating system is the one which needs to actually point out that the file which has assignment 6.c should be stored from disk 1 or from the on the disk block 1 to 100. That's what file system does. Okay, 2 levels of abstraction. One is what device gives to the file system, the operating system. Second one, what the operating system gives to the user. User thinks in terms of files and reading and writing to files. Files is the operating system, or file system as part of the operating system, thinks in reading and writing in physical blocks of secondary storage. Now, specifically for a hard disk, provides in-place rewrite and random access, and this I/O transfer performed in usually 512 bytes of blocks. So the blocks that I talked about in the previous slide that the operating system sees, that happens in the blocks of 512 bytes. Okay. So, but sometimes the block sizes may range from 512 by even 4 kilobyte from or larger. So any idea why the block size is not 1 byte? Because it will be most flexible for the hardware developers to actually just provide a block size of 1 byte. Any idea why it is 512 bytes of block? Oh, sorry. Srihash told too many I/O operations. True, true. Anything else? Yes. So this is the good. So Rutav actually get to the heart of it. I would say this not only, I mean, both Srihash and Rutav, that the higher size of blocks essentially means that you can ensure spatial locality, because you are basically reading or writing similar type of data, which will be accessed similarly at the similar place. And that would also decrease the number of I/O operations. So essentially, this is for performance improvement, but the spatial locality angle is, that, and both, I mean, that in turn would reduce the number of I/O operations. Because Sriyash, if it is like in a block, you are putting the data from multiple files, or you actually cannot, then either you have to do too many I/O operations on the same file on the same block for accessing multiple files, or you will be losing a huge portion of each block because there is not enough data to write. So this is based on the idea of spatial locality. And of course, bulk write works because there is the idea of spatial locality. Okay, this file system, essentially now we talked about the physical layer underneath the hardware that you bought. And then we also talked about the file system on top of it. So in general, file system actually goes into multiple layers. At the lowest layer, there are physical devices consisting of magnetic medium, motors, and controls, and the electronics connected to them and controlling them. This is like your hard drive that you bought, the box that you bought and put in your laptop. And modern disk put more and more of this electronic controls directly on the disk itself, and there are only a few things. I mean, very little work for the disk controller card to perform. So each disk comes with a disk, like actually the disk, and then an extra disk controller card, which is a very small, some mechanical, some electronic circuits to actually do this reading and writing and all those things. So these days, most of the bookkeeping of like different bits and bytes and error controls and all this more intricate stuff that is done on the drive disk itself rather than on the disk controller card. And then these devices are interfaced. So this hardware and that this is interfaced with the software via I/O control. So what is I/O control or input-output control? Input-output control consists of disk drivers, special, which are basically, how many of you heard of disk drivers or device driver, not disk, specifically hardware drivers, but in general, device drivers? Any of you have any idea about what a device drivers are? I mean, I know that some of you might have seen like driver co. I mean, there's like, you need to update your driver or is the right driver and so on. But any idea of what it is? What is a driver? Like in the I/O control, I told they're all about device drivers. Interface between hardware and OS, sure, yeah. And not only hardware and OS, hardware and between any firmware, like any software from hardware to the OS. That's true. Anything, any other characteristics of device, what a device drivers might be? Okay, so let me give you a hint, or rather what device drivers are. And remember this because often as computer scientists, we need to at least play around with device drivers, especially when you are getting a new hardware, specialized hardware for your research or for your industry. So what is device drivers are special softwares which are often written in assembly or sometimes a mix of C and assembly. This is what I have seen, C and .asm or volatile construct, if you know about it, but essentially assembly and C, which communicates with the devices directly. Devices might actually mean your hard drive or your sound card or your keyboard or anything of these devices. And how do they do that? Essentially by reading and writing special codes directly to the memory addresses corresponding to the controller card's registers. Remember that in any drive or device, you will have a small chip. So there is a mechanical part and then there is a chip. There is a card, device card, and the device cards gives you registers through which you can read and write information from that device. Okay, and essentially each controller card on a system has a different set of addresses, that is registers, because each controller has different registers, and these are called ports, device ports, that the device driver listens to, which actually means reading and writing special codes. So where do they get the special codes? That is given to them by vendor. And now today, if you are buying a keyboard from Mac and another keyboard from TVS, another keyboard from Gigabyte, all of them gives you a similar interface, like similar addressing system in their device driver. Same goes for a hard drive from Seagate or a hard drive from Western Digital. Okay. And the softwares, the device driver software's main work is to read and write from those registers. You see that why is it important? Because as a computer scientist, you will be given hardware and then asked you to write codes for it, or then build upon that. Sometimes, like in Google, I recall that there's a story that Jeff Dean had to, make the hardware bare bones simply because they are cheaper, and then write softwares which will interface with those bare bones servers. Bare bones essentially means that he basically stripped off most of the component except for the processor, motherboard, and RAM. So the basic, after the device driver works, like the software talks to the device and gives you, see what it does it give? Basically reading and writing to the devices. So it gives basically perhaps an array or a data structure of bits and bytes, basically bytes and blocks. That's what people generally do. They don't do bits and bytes anymore. They read or write to bytes and using blocks also. And the basic file system level works directly with the device drivers, the softwares that you need to write. So what is device drivers? Remember this. Device drivers, all its work is to actually know what are the ports or registers of the devices, and it knows that exactly how to read or write, what special commands to give for reading and writing to those devices. But who is it reading or writing for? It is reading or writing for the basic file system. And this file system works directly with these device drivers for retrieving and storing raw blocks of data without any consideration for what is in each block. It's basically a chunk of data, bits and bytes. And depending on the system, these blocks with the device, this basic file system reads and writes file using the device driver to the device. They might be referred with a single physical block number, for example, block number 1, 2, 3, 4, 5, 6. Or in older ones, like by single block number, what I mean is that remember that you have this for the operating system, for the device drivers, by virtue of this device controller card, you can see it only like you have a bunch of physical blocks from 0 to n. So in newer systems, it will be like write it into block number, write this date, write Shubham Misra or Sharuta Mitesh in block number 1, 2, 3, 4, 5, 6. That's it. But in the previous generation, in older systems, you actually need to write like what is the what is the sector number and cylinder number and what the head should go. Okay. Because controller cards were not good enough at those days. Now, this basic file system supports the file organization module. So, basic file system is basically just reading and writing these blocks of data. Nothing. And takes an input, where to write, what to write, where and what. And the file organization module knows about files and their logical blocks and how they map to physical blocks on the disk. In addition to translating from logical to physical blocks, the file organization module also maintains a list of free blocks, because the file organization module, this module, basically needs to know where to write the next bunch of data. So it also maintains a list of free blocks and allocates free blocks to new or existing files as needed. New files, you will assign a set number of blocks specific to operating system at the beginning, and then you will continue adding more and more blocks to a file. A file says a structure, a file is a data structure, so you can just say that I'm adding more and more blocks to it. You can do that. Now the logical file system uses this file organization module, and it deals with all the metadata associated with the file. For example, who created the file, like the name of the creator, the write or read or write mode, who can write what, and the date of the file ID, like basically everything about the file except the data itself. So if you follow the previous lectures, each file is like a book in some sense. A file system is like, or actually a file is like a book chapter. And even in book chapter, you have subsections, and this logical file system deals with the metadata associated with the file, but not the actual book chapter. It's like what the book chapter is, who wrote this, and what is an abstract perhaps, when it was created, and what are the references, how many figures are there. Such bookkeeping information are basically metadata associated with the file, but not the file data itself. That's what the logical file system does. Okay? So this level manages the directory structures in other words, right? And the mapping of file system file names to file control blocks. Now, you see, this logical file system needs to keep a bunch of data, a lot of data, metadata about each file. Who created this, what is the name of the file, when was it last accessed, what is, and a bunch of different other things. But they cannot really put it in like single variables. They need to create a data structure which would be replicated for each file. And this data structures essentially called this file control blocks, or FCBs. So essentially this FCBs are basically just like FCBs are same to files as PCBs, or process control blocks to processes. And FCBs very basically, you know, if you look into the attribute in the previous lectures, in the last lecture even we talked about the file attributes from name to everything. All of them are in a single database called file control block, FCB. And the FCB I talked to in the previous lecture that in earlier we know that in FCB essentially the file directory needs to know which where in the hard drive is the actual data stored. So now because we know about disk addressing now, so we can say that actually means that FCB in logical file system also contain the block number in modern operating system. Where is the data written? What is the start of the data? Because you just need the start address and the size. So you know the size in blocks and the number of data and where in the block does it start. That's what logical file system handles. So essentially the logical file system creates an abstraction over what files actually are. That is a bunch of your blocks along with some metadata. And this file control block, the storage structure constituting information about the file, is also called the inodes. Remember this name, inodes in specifically Linux, but they are basically file control blocks. Everything that you ever want to know about a file. Okay. Any questions about these different layers of file system? Because tomorrow, if you want to know about what is drivers, then we might have to, you know, as a computer science, you should know what actually mean by drivers rather than something that you download from internet. Any questions on these different layers of file system? Okay, so this layered approach to file systems, and feel free to write your questions in the chat box also, but this is simple. The layered approach to file system actually means that much of this code can be used uniformly for different file systems, and only certain layers need to be specific to an operating system. Okay? And there are multiple common file systems that you can choose in operating system. For example, you have Berkeley fast file system, Windows FAT32, that is in Windows, NTFS Windows specific, or you can have the extra ext2, ext3, all this, and journal file system in Linux. So you have to choose the type of file system when you are installing Ubuntu or any Linux distributions, and it supports around 40, I guess. 30. But in any case, my point being that this layered approach essentially means someone else will write the drivers you can download and you can put it there, and then this file, the logical file system, what data to store, and you know how to access that data, number of blocks, you can read at one given time. All those things differ slightly between these file systems, and we will come to that in this implementation in detail. But the whole point is that every single of this file system fits into this layered structure. You buy the devices from the vendor. It comes with a device driver that you download from internet or write from yourself that can read and write data without knowing anything else. It can read and write to the registers. And then the basic file system essentially takes help of IO control to write blocks of data. So you will get the block-wise reading and writing capability. And your file organization module essentially use the basic file system to actually create these files of like the data of these files, reading and writing and retrieving, deleting everything. And then this logical file system gives you the index. Up to file organization, you're reading and writing actual data. Logical file system gives you the index of this data in the files. Because each file, the most, like if if you see any file like a movie file, the most important thing is the data. However, without knowing the metadata, you cannot read the data. What is the format of the data? Who will tell you that? The metadata will. Is it MP4, AVI? What is the type? Tri-hype? I mean, the names of the files is not always correct. So the metadata that is maintained by the logical file system often gives you that hint. Any questions on the layered file system? These are the layers of file system. So let's move on file system implementation. So essentially, we have this. Recall that in your PintOS, you also saw that OS needs to implement open and close system calls for processes to request access to file contents. Now let's check the structures and operations used to implement the file system operations. No, so essentially, their functions have on disk and in memory structures. And these structures vary depending on the operating system, Linux, Windows, Mac, and the file system that you use, because even in Windows, you can use 40 different file systems. But some general principles apply, and we are going to talk about those general principles. That how that implemented, because in PintOS, for example, when you're implementing open and close file system calls, you have to use the hard drive given to you by the simulator. But in other, if you're running PintOS on other, in a computer, in an actual computer, it won't really hold. So it will change from, the platform, the operating system that hosts the file system. But the general principle is the following. There is in a file system, there's a boot control block that is in per volume, that exists per volume, which can contain information needed by the system to boot an operating system from that volume. So what it means is that if a disk contains an operating system, like your C drive in Windows, then essentially it will have a boot control block. It is typically the boot control block is the first block of the volume. And in Unix file system UFS, it is called the boot block. In NTFS, it is called the partition boot sector. The very first block on your C drive in NTFS is called the partition boot sector. Understood? So in a computer, there might be, you can actually install operating system, multiple operating system into multiple volumes. Right? And each volume that has a unique operating system that has a boot control block, generally the first block of volume. And in this boot control block contains information needed by the system to boot OS from the volume. Okay, now here's the question for you. What is this mysterious contains info needed by the system to boot from the volume? Use your imagination. What might be, like, what is that mysterious info that is in the boot control block, the first block of a volume, of a partition, essentially, in common language? to boot operating system from that volume. So Shubham told a magic number. Srihash told kernel loader. Any what? I mean, you're getting there. So a bit more specific. Be more specific. Others? Like what can be the mysterious information that the system needed to note of boot OS from that partition? So Srihash, what you told, so Shubham, when you told the magic number, what do you mean by that? You can unmute yourself and explain perhaps instead of writing a long answer.
I mean, sir, there must be a number in the first sector of the
First
block,
block. Let's not
first
talk
block,
about sectors anymore.
uh,
First block. Okay.
first block, such that when the bootloader tries to check if there is a OS in that volume, it will see that certain constant number to understand what if there is any OS or and what type of OS it is, so
Okay.
that it can list out and start loading the kernel from that volume.
Okay. Srihash, what do you expect from kernel as kernel loader? What do you mean that the first block contains the kernel loader?
Yeah, I was just thinking that maybe there was a pointer to the code that actually starts the kernel. So maybe something like an address.
True. Actually, both of you are correct up to certain extent, but Srihash was actually like hit the nail on its head. Uh, Essentially, the first block generally, I mean, so if you look into the BIOS, the firmware that doesn't require OS, but that comes with your machine. I hope that many of you played around the BIOS because we tend to break computers heavily. BIOS actually have which like what is the boot sequence, matlab, which hardware do you want to go to one after another for booting. So the computer just follows that, and essentially in the boot sequence you have the when you told the magic number, Shubham, you're partially correct, right? Yes, there has to be a magic number to tell like where the bootloader should start exacting from, but more specifically it's like what is the first instruction that you need to run on that block, like what is the address of the instruction. If that instruction is an invalid instruction, it will just fail and it will go back, and then the firmware need to handle it. In general, it shows sometimes a black screen of death, or it shuts down or do something. But essentially, if it is not a valid instruction, then the bootloader will know if the first instruction is valid. But it is basically the first instruction of an operating system or kernel, essentially. Now, moving away from boot control block, which is basic and most of you have seen it, even though you might not have realized the boot instruction. Like if you have a dual boot system, you definitely have played around with booting instruction. And then, aside from boot control block, essentially there is also a volume control block. Volume control block is again on per partition. It contains volume or partition details, such as number of blocks in that partition, basically how big is the partition, the size of each block, a free block count, because if you look into, again, in your Linux, if you do df or a command, or in Windows, you look into your disk utility, you will see how much space is free. How would they know it? Because the volume control block, which is per volume, that contains the volume details, which contain the free block count and pointers to those free blocks. Everything in the name of efficiency. Meaning that if you're in that partition, if you're creating a movie file, the free block, it will just go to this volume control block, or it's called super block or master file table, MFT. Okay, superblock is also a very, I really like the name. It is used in Linux. So it is basically superblock, which basically tells like, if I want to know that where should I write my 3 GB .mkv movie file, then the volume control block will just calculate and say like, I have this number of free blocks and each free block has this particular size, and here are the pointers, so you can write it there. And my file system will just write with the help of basic file system and device driver, will write in those free blocks. If the volume control block or super block is corrupted, then you don't really know information about your file system, and you often tell the file system itself is corrupted. Then you format the file system, remove everything in it, simply because if there is no index, then you cannot really retrieve any file. And or basically you can try by interpreting bits and bytes using very complicated heuristics, but for normal people you cannot. And essentially you partition, you format a drive, remove everything, make everything free, and create a new volume control block, which basically tells the number of blocks, number of free blocks, which is total size of the blocks, and pointers to free blocks. So in a file system, you have the special boot control block in the partitions, which are loadable, like which are bootable partitions. You have a volume control block, which has for any partition, not only bootable and unbootable, it has the master file table, which contains volume details. And then you have a directory structure per file system, which is used to organize the files. In Unix, this includes file names and associated FCBs, that is the numbers of the inode. What the numbers of the inode? So essentially, it in each partition or in each file system, in this case, which in each partition, so in each file system, you have a list of pointers to different file control blocks, array of pointers to file control. And this directory structure essentially in Unix includes file names and associated indices of those file control blocks in the array. Okay. So names and inode numbers, in particular for Unix, you have the inode name. So you call the FCB as inode. Okay. So it has directory structure constant names and inode numbers, which basically means pointers to the inode table or the master file table. What does inodes have? To recap, what does inode store? It stores information about the file, including ownership, permissions, and location of the file content. So these three things, boot control block, volume control block, directory structure, common across multiple operating systems, multiple file systems. Now let's look a little bit into this FCB, because this is a directory structure is something that you need to implement, right, as an operating system developer. So for each file, the file control block contains many details about the file. For example, the inode number, the permissions, like who can access, read, and write to the file, the size of the file, the dates associated with the file. Dates, why dates? Like, when the file was created, when it's modified, when it was last opened. All those information stored in the inode. In NTFS, this information is generally stored within the master file table, which actually in NTFS is like, it's basically the interesting, they use a relational database structure so that for ease of querying. So I'm assuming some of you at least know about the databases. For you that don't know, it's basically a huge data structure which can give you some very interesting, which can give you very efficiently answers to some queries. For example, find all the files with the file size 30 MB. In relational DB structure, you can write very nice human readable query codes to find those things. So this is the structure and content attributes of the file node, like file system, file disk, create, access, and write. File owner, who is the owner of the file, which group can read or write the file, and the access control list is also there, which you don't need to know what is about. Whoever you know, great, but not necessary. The file size and the file data blocks or pointers to file data blocks. So it can contain the file data blocks as say list essentially, or more commonly it it actually be a pointers to file data blocks. When I say that this FCB can have the file data box itself, that means that for each file you possibly take, say the file actually takes out 5 blocks of data, then you have a 6th block at the beginning. You append a contiguous 6th block at the beginning if you can, and that will be, and you put your information there. Okay. However, more commonly, you have pointers to file data blocks because they are all over the secondary storage. You don't need to have a contiguous space where the first block is the FCB and the rest of them are data blocks. That might not be necessarily true. And that gives you, that makes your operating system development really, really, really constrained. So so far, what do we know? We know about disk structure. We know the basic directory, bootable volumes, and what should be there in operating system. And we also know about FCB or inode, right, which contains information about the file, not the data of the file, but information about what the data is, who accessed it, what the permission is, and so on. Now let's talk about how does the file system related system calls work. So for create, and actually all calls of a file system and operating system needs a few data structures. And this includes an in-memory mountable, like in-memory mountable, like FS mounts or mount points or FS types, essentially which contains information about each mounted volume, because you need to know that where do the file system, each file system start. Remember what is mounting. So if you look into this additional 10 minutes or 15 minutes lecture, you basically say like mounting is that you have multiple file systems. For example, in my external hard drive, I have a file system and I want to add it to, using USB, I want to connect it to my laptop. So that file system needs to be added to the file system table that we already have. So to know that which different file systems are part of my the master file system where I will go to the different places, you have an in-memory mount table which contains information about each mounted volume, each mounted partition. And then you have an in-memory directory structure, which basically this is a directory structure cache, which holds the directory information for recently accessed directories. Remember the directory structure itself, the index that resides into your secondary storage on your disk, which means that it is slow, which means that you need some cache to put it in memory and make it faster. So an in-memory directory structure cache holds the directory information of recently accessed directories. So and then so first is in memory, that is it resides in the RAM, which have a mount table, like where everything is like information about this mounted volume and the start of that file system. Then you have an in memory that is that resides in the RAM, to make it more faster. It has a part of the directory structure for recently accessed directories. Remember, in some cases, if you have too many files, it takes too much time to look into all files in the directory because it is not cached. But when you are accessing that directory again and again, it becomes faster. That happens. And then you also have per process that's the system-wide open file table, which contains a copy of the FCB, the inode. Right. So to operating system, you just you like inode is the main representative of a file. You manipulate inode to do anything with the file. So there is a system-wide open file table which contains pointers to the inodes of the open files, and then there is also a per process open file table, which basically gives the pointers to the files opened by a particular process. So when I say open file table or anything in the operating system, for operating system, a file is basically a FCB and inode. Anything you want to do with the file data, you do it on inode. aside from exactly writing to the data blocks. But most of the operations for operating system is based on manipulating the inode. So in the system-wide, this open file table, as well as other information. So there are buffers to hold file system blocks when they are being read from the write and write. This is for performance. So essentially, you cache the file system blocks when they are being read from disk or written to disk. Okay. So these buffers, when you're saying like reading and writing to disk, what I mean is that a disk has a particular speed, right? 70 to 200 RPM or 550 Mbps per second write speed on all these things. But in general, aside from the hardware, so the operating system doesn't need to know what the hardware size is for writing. It has to be general enough. What does it mean? Essentially, it means that you would need the buffers, just like spooling. Remember that spooling essentially use virtual buffers to read and write to devices. It's just like that. Buffers actually hold file or file system blocks while they're being read from the disk or written to disk. An operating system talks to these buffers. It pushes data to buffers and takes data from the buffers. Okay, then. So I would stop here and we'll continue at 2 p.m. today. To start with, how does this different system calls, like create, open, and so on, works? Thank you. That will be all for today. But if you have any question, please feel free to ask. Stopping the recording.